Hi everyone, this is Junchong Fan from Center for High Performance Power Electronics at The Ohio State University. I'm a PhD student in Dr. Jing Wang's group. Now, I'm mainly focusing on high power density converter and cooling system design. So today, I'll introduce the development of liquid metal-based cooling for power electronic systems with inductor-integrated magneto-hydrodynamic pump. The demonstration will have three main parts. First, I will briefly introduce liquid metal-based cooling, the principles of magneto-hydrodynamic pump, and the newly proposed liquid metal-based cooling system. Then, the evaluation of the prototype and the test results will be shown. The last part is the summary of this work. As the power density of power electronics converters continues to increase, so does the requirement for heat dissipation capability. The combination of liquid metal and imaged pump is a good candidate for high-performance cooling system. Gallium alloy, which is in the liquid state at room temperature and non-toxic, shows great advantage compared with water coolant in terms of thermal conductivity. By replacing water coolant with liquid metal, a significant reduction of cold plates thermal resistance can be realized. In addition, liquid metal is electrically conductive, so Lorentz force can be applied to drive the fluid using an electromagnetic pump without rotating parts. Then, let me briefly introduce the principles of imaged pump. This non-mechanical pump can be used to pump electrically conductive fluid, such as salt water and liquid metal. Inside the pump, the Lorentz force is produced when the current is applied across a channel filled with conductive liquid metal in the presence of a perpendicular magnetic field. As shown in the diagram, the Lorentz force can be expressed as a production of a magnetic field, current, and channel width. This page shows the newly proposed inductor-integrated imaged pump, which can be shortened to I-square imaged pump. The operation principles are similar to regular imaged pump. Instead of using permanent magnets and external power supply, the I-square imaged pump utilizes a magnetic field produced by the inductor and the inductor current to generate Lorentz force. The diagram shows the critical components in the cooling system. The inductor in this case not only functions as a pump for the liquid metal, but also can be a critical part of typical power converters, such as the output inductor of a buck converter. The heat generated by switching poles will be taken to the radiator and exchanged to the ambient. This inductor-integrated design reduces the number of rotating parts in liquid-based cooling, and the pump does not require auxiliary power supply and permanent magnets. Moreover, the flow rate of the liquid metal coolant will be self-adaptive to the load condition. This page shows the details of the inductor design and the prototype for evaluation. The picture on the left shows how the Lorentz force is generated inside the pump channel, and the right figure is an overview of the prototype. As you can see, this is a 165 micron inductor, which integrates the liquid metal imaged pump inside. And the one on the left is the flow rate measurement unit. It utilizes the induced Fugit potential generated by liquid metal flow to indicate its flow speed. On the top is the buck converter. This is the heat source in the cooling system. And the last piece is radiator and the cooling fan. During the operation, the liquid metal coolant driven by the inductor integrated pump will bring the heat from converter to the radiator, and the heat will be dissipated to the ambient. So this footage shows the liquid metal flow during the operation. The evaluation results and comparison are presented here. The liquid metal coolant flow rate, estimated device power loss, and estimated junction temperature are plotted in the curve. These data are based on the measurement during the test. We can see that at full output power, the estimated device junction temperature is lower than 55 degrees C. Based on the measurement and calculation shown in the right figure, the power consumption of the pump is lower than 0.1 watt at 0.61 liter per minute, Meanwhile, the water pump consumes 4.2 watt at 3.7 liter per minute to reach the same junction temperature. Based on the evaluation and test results, we can say that the proposed liquid metal-based cooling system has several benefits, including better thermal performance, lower power consumption, and a smaller size. Also, it has lower acoustic noise and better reliability. And compared with DC MHD pump, the inductor with integrated MHD pump design eliminates the need for auxiliary power supply and permanent magnets, and the flow rate can be simultaneously adjusted according to the load condition. Active thermal management with essential magnetic components can be realized with I2 MHD pump. Because of the integration design, the I2 MHD pump can be a gateway for integration of electronic systems and cooling systems. This page is a preview of more comprehensive comparison between three types of cooling systems. More detailed and comprehensive comparison between liquid metal-based cooling with DC MHD pump, I2 MHD pump, and water-based cooling will be presented in the following WIFDA 2021, and the comparison results will be shown in the coming WIFDA paper. Finally, we would thank Dr. Madhu and Dr. Radha and the Department of Energy for their support on this work. Thank you. This is the end of my introduction.